All right, I'm not entirely sure why nobody showed up to our online class today, but I will go ahead and work an example problem that I intended to and post it on YouTube, and you guys can watch it if you find it useful. So the problem that we're going to work is going to demonstrate some of the complex power relationships that we will be utilizing for the remainder of the class, as well as the power factor correction relationship. So let's say that we have the following circuit. Our goal is to find the complex power supplied by the source, the power factor at which the source operates, the voltage Vs, and we want to know what size capacitor. So let's see, we want power factor at the source, complex power absorbed by the source. We want to know what the phasor voltage Vs is. And we want to know the value of the capacitor, which will make EFS equal to 0.9. All right, so the first thing that we are going to do here is we are going to find the complex power absorbed by our loads. So load 1 is the load which I'm saying is drawing a power of 20 kilowatts at a power factor of 0.7 leading. So we can say that S load 1 is going to be equal to the average power divided by the power factor, because that is the same as the apparent power, with an angle of negative inverse cosine the power factor. So this is going to give us our power factor angle. And the reason that we have a negative sign is because we know that the power factor is supposed to be leading, and leading power factors only occur when the phase angle of the complex power is negative. So if we substitute in the numbers from our circuit diagram, this is going to be 20 kilowatts divided by 0.7 with an angle of inverse cosine of 0.7, and this is going to give me 28.571 with an angle of minus 45.573 degrees kilovolt amperes. For load 2, we're given the apparent power. So our relationship to find the complex power is simply our apparent power for load 2, 12 kVA, with an angle of inverse cosine of our second power factor. So because we were given the apparent power directly, we don't need to divide anything by the power factor angle, or excuse me, the power factor. Also, we have a positive sign on our angle because our power factor is lagging, not leading. So from this, we're going to have 12 kVA angle positive inverse cosine 0.8. And that gives me 12 angle 36.870 degrees kilovolt amperes. And so our total complex power absorbed by our loads, which I'm just going to call S load, is simply S load 1 plus S load 2 which I get to be 32.411 angle negative 24.041 degrees. kVA. Now, our ultimate goal is to find the complex power supplied by the source. And if we look at our circuit, we've figured out what the complex power is absorbed by this load. We figured out what the complex power absorbed by this load is, but we don't yet know what the complex power absorbed by our transmission line is. And at present, we don't know what the voltage drop over our transmission line is, nor do we know what the current flowing through our transmission line is. So that's going to make things a little bit more difficult. However, we do have enough information to determine the current that's flowing into this node point where it will split and divide among the two loads. So we know that the complex power absorbed by a load or a combination of loads is equal to the RMS voltage phasor multiplied by the complex conjugate of the RMS current phasor. We can rearrange this expression and find that the complex current phasor is going to be equal to our complex power divided by our RMS phasor voltage, and then we take the complex conjugate of that ratio. So if we take the complex conjugate that's of the right-hand side, that's going to give us I phasor, not I conjugate, and we're looking for I phasor. So using this relationship, we can find pretty easily that the current flowing through our transmission line, which is the current that's going to flow into that node and split among those two loads that we already know the power of, will be equal to the complex conjugate of the total complex power absorbed by our loads divided by the RMS phasor voltage over our loads, and then we take the complex conjugate. So for us, that's going to look like 32.411 angle positive 24.041 degrees kVA, where I'm using the positive angle because I'm taking the complex conjugate of the numerator. And for my load voltage, it is 240 angle, we could call it -0, but it doesn't particularly matter. So I'll just put it 0 degrees here. Volts RMS. It is important to note, however, if our voltage had a phase angle, we would need to take the complex conjugate of both the numerator and the denominator. We don't just do it for the numerator. So if I perform this math, I get a current of 135.048 angle -24. Oh, sorry, angle positive 24.041 degrees. So let me just store that value in my calculator real quick because I'm going to need to use it. All right, so now I can determine the complex power absorbed by my transmission line. So the complex power absorbed by my transmission line is the voltage drop over my transmission line, which I don't know, multiplied by the complex conjugate of the current flowing through my transmission line, which I do know. But I can use Ohm's law and express the voltage drop over my transmission line, V wire, in terms of the current and the impedance. So V wire is simply I wire times Z wire. And this will be multiplied by I wire conjugate, which I could further simplify as I wire conjugate times I wire times Z wire, which finally is just the magnitude of I wire squared times Z wire. So that would be 135.048 amps RMS, quantity squared, and I apologize for not putting my units over here, multiplied by the impedance of the wire, which is 0.05 plus J 0.2. And if I perform this math, I get 3.760 angle positive 75.964 degrees kilovolt amperes. So now I'm in a good place to determine the complex power supplied by my source. And I say that because the complex power supplied by my source must be the sum of the complex powers absorbed by the loads in the transmission wire. So that would be S load plus S wire okay, hold on. $31.973 angle negative 17.391 kilovolt amperes. So that's my complex power supplied by my source. I can now easily figure out what the power factor is. So the power factor at which my source is operating is simply going to be the cosine of that angle, negative 17.391 degrees. Which I get to be 0.95 leading and lastly my phasor voltage Vs. I can use my relationship for complex power much like I did to find the current through my load, and I will find that Vs is simply SS divided by I wire conjugate. So that would be 31.973 with an angle of negative 17.391 degrees kilovolt amperes. divided by the complex conjugate of my current, which is 135.048 with an angle of negative 24.041 degrees amps RMS. Looks like 236.756 with an angle of positive 6.65 degrees volts RMS. So in this example, we've just applied our complex power rules and used our circuit analysis intuition to develop relationships here, and been able to solve for three quantities with really a very minimal amount of information. So let's work one more example problem. Where we will apply the principles of power factor correction. Okay, so let's say that I have a source connected to a transmission line connected to a motor. And my transmission line has an impedance of 1 plus J 0.5 ohms. My motor has an impedance of 5 plus J 10 ohms. And my voltage source is supplying 400 angle 0 degrees volts RMS at a frequency of 50 hertz. I want to know the value of the capacitor C that I should put in parallel with my source to cause my source to supply power at a power factor of 0.975 lagging. So C is equal to what at PF new is equal to 0.975 lagging. All right, so in order to determine how much, to determine what the capacitor needs to be to give us this new power factor, I need to figure out what the old power factor is to begin with, which means I need to know how much power, complex power, the source is supplying. So it should be fairly obvious that let's call this current here I source. If I know this current I source and I know the voltage supplied by the source, I should be able to figure out the complex power supplied by the source. So I source will be 400 angle 0 degrees volts RMS divided by the total impedance of our transmission line and motor combined together, which in our case would be 6 plus J 10.5 ohms. .076 with an angle of minus 60.255 degrees amperes. So the complex power supplied by our source prior to power factor correction is simply the RMS voltage times the complex conjugate of the RMS current is 400 angle 0 degrees volts RMS multiplied by 33.076 angle negative 60.255 degrees amps RMS, and then I conjugate this guy, so that's going to take that negative sign out, and I get 13.230 angle positive 60.255 degrees kilovolt amperes. My power factor, let's see. Actually, I don't even need to figure out what that power factor was. I have the complex power, so that is enough information. But I should express it in rectangular coordinates as well. That's going to be useful to me. So in rectangular coordinates, this looks like 6.564 plus J 11.487 kVA. Now, let's see. My power factor after my complex power after power factor correction is going to be the average power before power factor correction, because power factor correction holds the average power to be constant, divided by our new power factor with an angle of the inverse cosine of our new power factor. So that's going to be 6.564 let's see, kilowatts divided by 0.975 with an angle of inverse cosine 0.975. and I get that to be 6.732 with an angle of positive 12.838 degrees. Kilovolt amperes, or alternatively 6.564 plus J 1.495 kilovolt amperes. All right, so now I have enough information to determine my capacitor value, or very nearly it. So we know that the complex power supplied by our capacitor is S new minus S old. Which is negative 9.991, negative J 9.991 kVA. From this, we know that Q capacitor, the reactive power, is then negative 9.991 kilovolt amperes reactive. C, the capacitor value, is negative Q cap divided by omega times the RMS voltage drop over the capacitor squared. So this is negative 9.991 kilovolt amperes reactive divided by omega, which is 2 pi times 50 hertz times our voltage magnitude, 400 volts RMS squared. And so from this we get zero point 0.1987, so 0.198769 farads, or 198.769 millifarads. So it's going to take a rather large capacitor to correct our system up to a power factor of 0.975 lagging. All right, so those two examples have shown you all how to use the complex power relationships as well as how to perform power factor correction. So hopefully they're a good supplement to the lecture material that's posted. You all have an exam on Monday, so there will not be a class meeting. So I will see you all on Tuesday morning.